Central processing units, or CPUs, are the brains of our modern world. They power almost every electronic device we use daily. Think about your smartphone. It has a CPU. Your computer relies on one too. Even your car might have several CPUs helping it run smoothly and safely. These tiny chips perform billions of calculations every second. This incredible speed allows us to connect, create, and learn in ways unimaginable just a few decades ago. Without CPUs, the digital revolution simply would not have happened. They are the silent workers, the unseen heart, pumping information through the veins of our technological society. The importance of these chips cannot be overstated. They manage complex systems in industries like healthcare, finance, and transportation. Imagine a hospital without computers to manage patient records or medical equipment. Consider air traffic control systems trying to guide planes without powerful processors. The smooth operation of these vital services depends heavily on the reliability and power of CPU chips. Their development has been a story of constant innovation, pushing the boundaries of what is possible in science and engineering. The main ingredient for a CPU chip is silicon. Silicon is a very common element found in sand and quartz. However, the silicon found in nature is not pure enough to make computer chips. It needs to be refined to an incredibly high level of purity. This purification process is the first crucial step in chip manufacturing. The process begins by taking quartz sand, which is silicon dioxide. This sand is heated to very high temperatures in a furnace, usually with carbon. The oxygen in the silicon dioxide bonds with the carbon, releasing the silicon. The result is metallurgical-grade silicon, about 98% pure. To reach the required purity, the silicon undergoes further chemical processing. One common method involves converting the silicon into a gaseous compound like trichlorosilane. This gas is purified through distillation, separating it from most impurities. The purified gas is reacted with hydrogen gas, depositing as solid, highly pure polycrystalline silicon or polysilicon. This material is exceptionally pure, often reaching 99.9999999% purity. This ultra-refined material is the true starting block for creating the wafers upon which CPUs will be built. The journey from common beach sand to this ultra-refined material is a testament to chemical engineering. Once the ultra-pure polycrystalline silicon is ready, the next step is to transform it into perfect large crystals. This is usually done using the Czochralski method. Chunks of pure polysilicon are melted in a quartz crucible at over 1,400 degrees Celsius. A small seed crystal of silicon is dipped into the molten silicon. As the seed is slowly pulled upwards and rotated, the molten silicon cools and solidifies around it. This process forms a perfect cylindrical single crystal called an ingot or bulo. These ingots can be very large, sometimes over 2 meters long. The ingot is then ground to a precise diameter and sliced into very thin discs called silicon wafers. Diamond-edged saws are used for this cutting process. Each wafer is typically less than a millimeter thick. The wafers undergo several stages of lapping, grinding, and polishing to create an almost perfectly smooth, mirror-like surface. This polished surface is crucial because the circuits built on the wafer are incredibly small. The result is a pristine, ultra-flat silicon wafer, the perfect canvas for building hundreds or even thousands of CPU chips. With a perfectly polished silicon wafer ready, the next major step is photolithography. Photolithography uses light to transfer a geometric pattern from a mask to a light-sensitive chemical, called photoresist, on the wafer. This process is repeated many times, layer by layer, to build up the intricate three-dimensional structures of the transistors and interconnects that form the CPU. First, the silicon wafer is coated with a thin, uniform layer of photoresist. The wafer is then moved into a machine called a stepper or a scanner. This machine aligns a photomask very precisely above the wafer. Ultraviolet light is shown through the photomask, exposing the photoresist below. The pattern on the mask is a highly magnified version of the circuit features, and the optics in the stepper shrink this pattern down onto the wafer surface. After exposure, the wafer is developed, washing it with a chemical developer solution. If a positive photoresist was used, the areas exposed to light become soluble and are washed away. If a negative photoresist was used, the exposed areas become hardened, and the unexposed parts are washed away. What remains is a pattern of photoresist on the wafer surface, perfectly mirroring the design from the photomask. This patterned photoresist layer now acts as a protective stencil for the next steps, such as etching or doping. Once the photoresist pattern is in place, the next crucial step is etching. Etching removes material from the areas of the wafer not protected by the photoresist. There are two main types of etching: wet etching and dry etching. Wet etching uses liquid chemicals, typically acids, to dissolve the exposed material. Dry etching, more commonly used for modern fine features, uses gases in a plasma state to remove material with greater precision and control. The wafer is placed in a vacuum chamber and gases are introduced. Radio frequency power is applied, creating a plasma. Ions from the plasma are accelerated towards the wafer and physically bombard the surface, while reactive chemical species in the plasma also react with the material to remove it. After etching, the remaining photoresist is stripped away, revealing the newly patterned layer on the wafer. This sequence, applying photoresist, exposure, developing, etching, and stripping, is repeated many times. Each repetition creates a new layer of the CPU's complex circuitry. Another vital process is doping, introducing tiny, controlled amounts of impurities into specific regions of the silicon to change its electrical conductivity. Throughout the complex manufacturing process, testing and quality control are paramount. Automated optical inspection systems scan the wafers for defects. Specialized metrology tools measure critical dimensions, ensuring they are within tight tolerances. Once all the layers of circuitry have been built, a crucial electrical test called wafer sort is performed. A machine with very fine needles called a probe card makes temporary electrical contact with tiny pads on each individual die. The tester runs a series of electrical tests on each die, checking its functionality. Dies that fail the tests are marked or recorded electronically to be discarded later. The percentage of good dies per wafer is known as the yield. Higher yields mean more functional chips and lower manufacturing costs. This rigorous testing ensures that only functional dies proceed to the next stages of assembly and packaging. The dies that pass these demanding electrical examinations are ready to be separated from their neighbors on the wafer. After wafer sort identifies functional dies, the next step is dicing. The wafer is thinned, mounted on sticky film, and cut with a high-precision saw. The saw uses a diamond blade to cut along scribe lines. After dicing, dies are held by the sticky film. Good dies are picked and moved to packaging. A vacuum tool or gripper places each die into a tray or substrate. This step is crucial before the dies become the brains of electronic devices. Once a die has been cut from the wafer and confirmed to be functional, it needs to be packaged. Packaging provides a robust physical casing to protect the delicate die from mechanical damage and environmental factors. It also provides the electrical connections that link the microscopic circuits on the die to the much larger printed circuit board in a device. The first step in packaging is usually die attachment. The individual die is mounted onto a substrate, which is a small circuit board that forms the base of the chip package. The die is typically attached using a special epoxy adhesive that provides good thermal conductivity. Next, the electrical connections are made between the die and the substrate. This is most commonly done through a process called wire bonding. Extremely thin gold or copper wires are used to connect each tiny electrical pad on the periphery of the die to a corresponding pad on the substrate. An alternative method, especially for high-performance chips, is flip chip technology. Finally, the die and the wire bonds or flip chip connections are encapsulated. This encapsulation protects the internal components and provides structural integrity. The journey of CPU manufacturing has been one of relentless innovation and miniaturization. The first commercially available microprocessor, the Intel 4004 released in 1971, contained about 2,300 transistors. Today, high-end CPUs can boast tens of billions of transistors on a similarly sized piece of silicon. This incredible increase in transistor density is famously described by Moore's law. Key innovations have fueled this progress. The development of photolithography techniques using shorter wavelengths of light has allowed engineers to draw ever finer circuit lines. Improvements in material science, such as the introduction of copper interconnects and high-K dielectrics, have been crucial. FinFET transistor architecture was a major breakthrough enabling continued scaling. Looking ahead, the path to even more powerful CPUs faces new hurdles. Researchers are exploring new materials like graphene or carbon nanotubes, and new computing paradigms such as quantum computing. Chiplet technology is also gaining traction as a way to continue improving performance and functionality. The future of CPU manufacturing will likely involve a combination of continued scaling, innovative packaging techniques, new materials, and perhaps entirely new ways of computing.